Hello dear colleagues, my name is Alexey Dolgov and I'd like to present my scientific report on the theme Evaluation of qualitative indicators of the mathematical model of thermal tomograms construction based on the data of different time infrared images. One of the areas of advanced development in the field of the data processing from unmanned aerial vehicles is the integration of intelligent systems and methods of the theory of computational thermophysics. Conducting an aerospace survey in the conditions of polygon tests of one area for a long time allows you to record the dynamics of processes occurring on the air surface in the visible and infrared wavelengths. Therefore, the use of robotic systems with a long flight duration has led to the development of new approaches to processing a set of images obtained at different time intervals. One of these approaches involves the use of periodic survey of the area in the infrared range to obtain a set of infrared images, a cuboid of infrared images, that reflects the dynamics of temperature changes on the surface of the studied area. Processing of the cuboid of infrared images allows you to select areas with similar dynamics of changes in thermal contrasts. The presence of materials with known thermophysical parameters on the image reference test objects made of materials with known parameters allows you to identify areas where the dynamics of change in thermal contrasts was close to the specified reference test objects. For computer implementation of these models, an algorithm has been developed for obtaining a stochastically regularized solution of the coefficient inverse problem of thermal conductivity, which belongs to a compact set of acceptable models, providing the formation of a database of thermal tomograms of analogous objects and underlying surfaces. In order to check the adequacy of a constant mathematical model and its corresponding algorithmic implementation, the paper considers the problem of evaluating the qualitative characteristics of the model, such as adequacy, stability, and sensitivity. In general, the models under consideration belong to Hess class of stochastic nonlinear models of the state space. The state space model is usually obtained using the law of the first principle, such as mechanical, electrical, or thermodynamic physical laws, and the identified parameters usually have some physical meaning or significance. A model of the state space with discrete time can be defined using difference equation number 1 on the slide. We will check the quality characteristics of the mathematical model that implements the construction of multi-layer thermal tomograms based on the field experiments using reference materials with known thermal parameters. Two independent field experiments were conducted in different seasons of the year, in autumn and in summer, in order to obtain thermophysical parameters estimated of reference materials and to test the mathematical model for constructing thermal tomograms in a different range on input parameters. The area of field experiments with reference materials is present at figure 1. Areas of the EF surface with reference materials were exposed to natural solar heating during the day. The obtained infrared images of these regions were formed into cuboid, and the inverse coefficient problem of thermal conductivity was solved for the interior raster of these images. Graphs of the dynamics of temperature changes on the surface of reference materials experimentally measured and calculated by numerical simulation using MATLAB and GIDRUS 1T software, and the convergence or the genetic algorithm for solving the inverse coefficient problem, thermal conductivity, are present at figures 2 and 3. To check the adequacy and stability of mathematical models for construction thermal tomograms, a set of thermal tomograms of the EF surface areas with reference materials was obtained, presented at figure 1. Calculated at the same input parameters, and samples were made of the values of thermal activity of each reference material for the summer and autumn experiments. Thermal tomograms of reference materials are present at figure 4. To check the adequacy of the mathematical model to the behavior of the original, it's enough to make sure that two properties are met: accuracy and consistency. To check the accuracy of the mathematical model to the original, we show that the mismatch of the thermal activity parameter of the reference material are obtained using numerical calculation is not higher than the set value of the acceptable error of 10%. The results of measurements of thermal parameters of reference materials and background are present at table 1. The relative error of measuring thermal activity does not exceed 10%, which corresponds to the set value of permissible error. Consistency implies that the output parameters are changed identically. From the central limit theorem follows a universal method for checking consistency. By checking whether the mismatch is subordinate to the error law. In other words, in order for the mismatch between the original and the model to not describe any regularity, the mismatch must behave quite chaotically. In other words, obey the normal distribution law with zero mathematical expectation. Based on obtained samples, the probability densities of thermal activity of the reference materials are constructed. Figure 5. We will check whether the obtained values of thermal activity of reference materials belong to the normal distribution law using the Pearson criterion based on the solution of the problem of statistical hypothesis testing. As the main hypothesis, we will assume what the obtained statistics are distributed according to the normal law, and as an alternative, we will assume that the statistics do not belong to the normal distribution. The values of the chi-square parameter of thermal activity of reference material are present at the table 2. From the analysis of the table data, it can be seen that for all reference materials in both experiments, the values of the thermal activity of the reference materials are distributed in accordance with the normal distribution. Thus, the adequacy of the mathematical model for constructing thermal tomograms based on the dynamic infrared images is proved. We will prove the stability of the method of constructing thermal tomograms by testing the hypothesis that samples of thermal activity of reference materials obtained under different input parameters such as meteorological, physical, and geographical conditions, as well as the time of day of infrared survey, have the same statistical future. That is, they belong to the same general population. To test the hypothesis about the stability of the results, we use the Wilcoxon test, which is used to compare and evaluate the difference in the values of two pair samples of the parameter under study, obtained under different conditions or at different times. Samples were obtained for the reference material soil in the experiment on 19th of July 2019 with small change in meteorological parameters. Table 3. As proof of the stability of the mathematical model for constructing thermal tomogram based on dynamic infrared images as television images, it's proved that the samples of thermal activity values obtained with small deviation up to 10% of meteorological parameters percent at table 3 belong to the same general population by solving the problem of statistical hypothesis test based on the Wilkinson criterion. As the main hypothesis, we assume that the sample of the thermal activity of the reference material soil present at table 3 belong to, and as an alternative, do not belong to one general set of values of thermal activity of these reference materials. The results of checking whether these samples belong to the Wilkinson sin rank criterion and the significance level are present at table 4. From the analysis of the obtained values of the probabilities of coincidence of samples of thermal activity of the reference material soil, we can conclude what were on ground for rejecting the main hypothesis that these statistics belong to one general population. And we can conclude that the mathematical model of building thermal tomograms as a whole is stable. We will test the sensitivity of the mathematical model based on its ability to respond to small changes in input parameters. For this purpose, we obtained is an estimate of the thermal activity of reference materials based on the data in the table 3. Graphs describing these dependencies are present at figure 6. Conclusion. While the scientific significance of solving the problem is determined by the contradiction between the need to provide information about the spatial distribution of anisotropic media, low visibility critical objects in the course of solving remote monitoring problems in the optical wavelength range, and the existing practice of analyzing data of individual infrared signatures of the Earth's surface. The evaluation of the qualitative characteristics of the mathematical model presented in this paper allows us to conclude that then the deviation of each of the input meteorological parameters increases from 5 to 10%. The values of the output parameter, thermal activity, change. For air temperature up to 30%, for relative humidity up to 5%, for wind speeds in the ground layer up to 10%, and for cloudiness up to 10%. This may indicate the sensitivity of the mathematical model for constructing the thermal tomograms to a small change in the input parameters. The literature is present on the slide. Thank you for your attention.